Christian Reitwiessner. Thank you for giving me the opportunity to give this talk here. I'm sorry that I can't be with you in person, but yeah, I hope you'll like my talk anyway. I would like to talk to you about the latest features of Solidity as a language and of the compiler, and we will also talk about current challenges and upcoming features we want to add next. Yeah, we'll start with the IR pipeline that we recently released or declared stable. Then about errors and encoding, the immutable keyword, then something I'm really excited about, the user-defined value types. And this leads up to generics that we want to add to the language, a standard library that will make heavy use of the generics. And in the end, I want to talk to you a little bit about how we plan to optimize memory. And one candidate for that is reference checking. So let's start with the IR pipeline. We declared this, so this has been in the works for quite a while. We started to use it for the ABI encoder v2 way back. And it is feature complete for, I think, at least a year now, and we declared it stable in March. What I'm actually talking about is a parallel code generator pipeline that uses an intermediate language and does not go to EVM directly as the first implementation of the code generator does. And the benefit is that this gives us way more flexibility. It also allows you to audit the code the compiler generates, so you can actually take a look at the assembly code the compiler compiles a smart contract to before and after optimization, which is really cool. And it also allows us to have way more opportunities for optimization. For example, we can do cross-function optimization, which is not really possible with the old way we did it. And currently we have comparative or in many cases better gas costs for the smart contracts. One tiny drawback currently is still that the optimizer is a bit slow on the ULIR, but we're working on that, and yeah. Oh yeah, and one final note, if you want to take a look at the optimized intermediate representation, then use as you see in the third line here, use the switch IR optimized to request the output, but you also need to activate the optimizer using -- optimize, otherwise the optimized output looks the same as the non-optimized output. Then just quickly about errors and encoding. These features are a bit old already, or I mean, not so recent at least, and you probably know about it. So you can define errors that take structured data as arguments, and you can use them in revert statements. So you can provide structured data to the caller, who then can analyze a bit better why some operation failed. We have bytes.concat that can be used to concatenate byte arrays and strings. We also have byte array slices now. And there's a feature or a function called abi.encodeCall, which takes arguments to be encoded for a function call, an external function call. And the benefit over what we had before is that it takes the function as an argument, so the compiler can perform type checking on the arguments and so that they match the parameter types of the function, and it reports an error if they don't match. Okay, now on to the immutable keyword. This is a nice way to declare a state variable to be constant, but only after the construction. So you can have an immutable variable that depends on constructor arguments, or for example, on msg.sender, like the owner variable here. So this is a token that has an owner, but we know that the owner will not change over the lifetime of the token. So we assign it msg.sender in the constructor, and the Ethereum virtual machine actually enforces that the variable does not change. The way this is implemented is very efficiently, because we do not take up a storage slot for these variables. but instead the value that is determined in the constructor is actually copied to the places in the code where this variable is used. This makes it extremely cheap and yeah, safe at the same time. Now, yeah, onto one of my favorite topics, user-defined value types. Let's start with a bit of a motivation. So we have a function here called approve that takes a token ID, an amount, and a start date. And currently, the best types you can find, or before we had user-defined value types, the best type you can find for these parameters are unsigned integers. So we take 3 unsigned integers here. And then later, when we call the function, we call it with amount, start date, and token ID, which is, of course, yeah, the variables are swapped around here, and this will have very bad consequences. But the compiler, it doesn't complain because in the compiler's view, everything is right. So the types all match, so there's nothing it can do. And it would be much better if we had different types for the different kinds of data here. So for example, in the second part here, we have a token ID type for the token ID, a DAI amount type for the amount, which also gives you a way to say what kind of amount it is. So is it a DAI amount or an Ether amount or whatever? And a date type for the start date. And now if you have a parameter ordering confusion here, then the compiler will give you a type error. So this is a really nice feature, but the question is it also cheap? And that is a clear yes. And this is because, so you were able to do something like this already in the past by using structs, but structs are always allocated in memory, so they are quite expensive and also have these reference semantics, which are a bit complicated to use maybe. So we introduced a way to define a new type that is stored on the stack. So these new types are always value types. And you have to provide an underlying value type it is kind of built out from. So you write token ID is uint, and this creates a new type called token ID, which is stored on the stack. And it's, yeah, all its internal semantics, so the memory layout, the storage layout, and so on, is taken from uint, so from the underlying type. But that's the only relation it has to the underlying type. It's it's a completely fresh and new type. It doesn't have any functions. It doesn't have any conversion rules. It doesn't have any operators, nothing. These are all things you can add your own later on. So the only thing that the compiler provides is a specific conversion function between the underlying type and the new user-defined value type. And this is called, these are the functions wrap and unwrap. And they are defined on the type word itself. So here we are building our own custom fixed point type, and it's a 128-bit type, and the underlying type is uint 128, and we define a function called uIntoFixed. And here, especially for fixed point types, there are 2 ways to convert from an unsigned integer to a fixed point type. The first conversion is just the kind of raw conversion of the underlying type to the fixed point type itself, where nothing changes. But this is usually not what you want for the user. What you want for the user is if you have a function and you input 1, then the result should be the fixed point type 1. So you have to scale this 1 by the fixed point type multiplier. And that's why and you can use, as I said, this fixed.wrap for the underlying raw conversion, but this conversion is something that you usually should not expose to the users. The user should only use this uIntoFixed and not care about what the underlying encoding is. One final comment to this for this type token ID is uint. This is not a type alias, so you can have as many new user-defined value types based on uint as you want. So this is just the relation to define the underlying encoding. So now, now we have defined the type itself, and we can add functions to the type as follows with the using statement. The using statement that already exists to add library functions to types. Or library functions or file level functions, and you can use that to just add them to the type as you're used to. And we also have a new cool feature for the using statement, which is this global keyword at the end. This adds these functions to the type globally in the whole project. And you do not need to repeat the using statement when you use global. The main restriction for global is that you can only use it for types you defined yourself, and you can only use it in the same file where you define the type. So the idea is that you have a module that defines a type, and you also define the functions the type takes, and then use this global keyword to just permanently fix these functions to the type. And then wherever you can use the type, the functions are also available. And when you have an external module, you're not allowed to add new functions on top, at least not globally. Yeah, I won't go through this code in detail. It's just, there's an example where you have in a different file, you have the function square, and it can just use x mul x without actually importing this mul function from anywhere. And this is nice, but of course, x mul x looks horrible. I mean, many people in this space are probably used to this by now, but I still think it looks horrible, and it's very, very hard to audit, especially when you have such nested operators. And that's why we also want to add user-defined operators as a feature. These are added to existing types in a similar way as functions are, but you just have this as operator. So using add as plus for fixed global, this or using mul as star for fixed global makes the multiplication operator globally available for the fixed point type we have defined, and it calls the mul function. So we have a function called square here, and we just write value times value. So of course there is always the criticism that this of course makes it more readable, but also more complicated, because you don't always really know which function is called for this multiplication operator. But we are working on the language server, and as soon as we release these user-defined operators, we will also release the language server, which allows you to do just control-click on the multiplication symbol, and then you jump to the function that is called. Another feature is what we're working on is a literal suffix notation that allows you to easily use constants with your user-defined types. So you can write things like value times 1.15 underscore f, and this will then call this underscore f function on this constant 1.15. There's a little complication due to the encoding of fractional numbers that we will provide extensive documentation on when we release the feature. One open question here still is how we declare these suffix functions to actually be suffix functions. If you have any input there or have an opinion, then we welcome you to our discussion forums. Then onto the standard library. So the standard library we are working on is not meant as a standard library that has like standard token implementations or these smart contract templates you usually use, but instead we want to take functionality that is currently baked into the compiler and extract it into a library that is actually written in Solidity and can be read and understood by people who know Solidity. So for example, there's currently this magical global function called addmod, which is modular addition, and it's available everywhere, which is also weird. So with the standard library feature, we will also have the requirement that you need to import all these globally available functions explicitly from the standard library, and then This addMod function will be implemented in the file std/math.sol like this. So it will drop down to inline assembly, of course, because at some point you have to reference the built-in opcodes. And the cool thing here is currently when you wonder what happens when you use addMod with 0 as modulus, does it revert, does it return 0? And currently you have two options. You either look in the documentation or you look in the compiler source code. But this is both a bit, I mean, you're writing Solidity code all the time, so it's much better if you see the Solidity code and see, oh yeah, it just has this require modulus is not 0 check at the beginning, and then you also see which kind of revert it does, whether it provides data together with the revert or not. So I think this is a really cool feature. And of course, we won't get very far with the standard library without a mechanism to write generic code. And this is another thing we're working on. It will, of course, not only be available for the standard library, but also for user-defined code. And we're currently leaning towards a mechanism that is rather strict than loose. So we want to have a mechanism similar to how Rust handles generics, in the way that, for example, here you have a max function, and it takes two generic parameters, but it requires that the type of these parameters implement a comparison function. And this allows us to do full type checking at the point where we type check the templated function itself, instead of only at the point where the function is used. So C++ has this weird mechanism where it only type checks the template at the point where it's used and not at the point where it's defined. This makes it a bit more complicated because we have to introduce all these notions, comparable, maybe copyable, and whatever. But I think this additional work is worth it. Here, the main open questions is how to handle the data locations, because you can't have mixed data locations, so you can't have a storage array that has memory pointers. So the storage location is rather tied to the variable instead of the type. And there's also the question whether or not you want to have implementations that are generic over the storage locations. So, for example, this max function here, you probably want to be generic over the storage locations because there's no other way you would implement it. But appending to a resizable array, there it makes a big difference whether it's a storage array or a memory array. Okay, then the last topic. When Solidity was initially designed, we were mostly thinking that transactions would be kind of short-lived, short-running, with only a little gas, and they won't do much. But yeah, this has changed a little in the past, and smart contracts are getting more and more complex, and they're using more and more memory. So in the beginning, we thought, we can just allocate memory and never deallocate because it will be cleared in the next EVM call frame anyway. And now it looks like it is worthwhile to think about a better memory allocation mechanism. So I have an example here. We have a loop, and this loop fills a storage array with structs. In the current implementation, this struct constructor will create a struct in memory and then copy it over to storage. And the bad thing here is that it will create a new struct in every loop iteration. And of course, it could just reuse the memory location of the previous iteration. And in this special example, all the structs are equal, so it's even the same content in memory all the time. So this is one of the first things we're working on: determine lifetimes of memory objects and deallocating them, or at least allocating them in a special buffer that can be reused or something like that. So, and a big open question here is, or a research topic, what is the balance between implementing a more complicated allocator that is kind of also looking for places to allocate memory and deallocate memory, and the additional overhead it has compared to the memory it saves. Okay, we always welcome anyone who would like to participate in language design. If you have ideas or comments or problems, then you're welcome to join in the discussion. We also really welcome people who help us prioritize issues. Yeah, how you can contribute can be found in our documentation. We also have weekly meetings on Monday and Wednesday, which are always open to the public. So you have any comment, just hop onto our meeting and talk to us. Other things we do is one-to-one feedback sessions, where we reserve some time to talk with one person about what they think about Solidity. We do the yearly user survey in December, so please participate in that. And yeah, we have a forum and a chat to talk, and we'll be happy if you follow our Twitter account. So thank you so much for your attention.